Module 18, Chapter 22. Now let's turn our attention to carbon dioxide transport. CO2 is produced by your body cells during aerobic respiration, and it's going to be transported in your blood in three different forms. About 5% of your CO2 is going to be dissolved in plasma. Another 5% is going to be transported as a carbamino compound. Recall from the blood chapter that CO2 can bind to hemoglobin, specifically the globin portion of your hemoglobin, and that when CO2 is transported by your hemoglobin, it's called carbamino hemoglobin. The other 90% of your CO2 is transported as carbonic acid. Now, the equation that you see on the screen is actually describing the chemical reactions that we're going to be talking about on the next two slides. If you take CO2 and water and combine them, you form H2CO3, which is called carbonic acid. Carbonic acid then dissociates, breaks apart into HCO3, which is bicarbonate, and hydrogen ions. The double-headed arrows in the equation show that this reaction is reversible, meaning it can head from right to left, or it can go from left to right, depending upon the chemical environment at the time. So let's talk about carbon dioxide loading first. So we're dealing with our systemic gas exchange. In carbon dioxide loading, carbon dioxide moves from your tissue and into blood. Once in blood, it's going to react with water to form carbonic acid within your red blood cells. So imagine your CO2 crossing into your blood, entering a little red blood cell, reacting with water to produce carbonic acid. Now, this reaction is catalyzed by the enzyme carbonic anhydrase. Now, carbonic acid then dissociates inside the red blood cell into bicarbonate and hydrogen ions. Once this happens, there's going to be something called a chloride shift. Chloride ions are pumped into the red blood cell, while the bicarbonate is pumped out of the red blood cell. Bicarbonate is very water soluble, so you can actually put that bicarbonate out into your plasma and it's very easily transported. Most of the hydrogen ions that are formed inside the red blood cell bind to hemoglobin, which is going to help buffer your intracellular pH. Now, our red blood cells are bicarbonate ions. They have flown through our venous circulation. We have arrived back in our pulmonary capillaries. And now we're going to do some carbon dioxide unloading. Now, what's going to happen is the reaction we did to load our CO2 is going to occur in reverse, meaning oxygen is going to be moving from alveolar air and into our wee little red blood cell. The oxygen is going to be loading onto our hemoglobin, which causes our hemoglobin to release the hydrogen ions that it was currently buffering. So our hydrogen ion concentration goes up inside the red blood cell. We're then going to do a reverse chloride shift to move chloride ions out of our red blood cell and at the same time bring our bicarbonate ions back in. From here, we're going to do a hydration reaction, causing our chemical reaction to occur in reverse, reforming our CO2 gas, allowing it to move from our red blood cell across your respiratory membrane and into your alveolar air. Now, that was how we transport the CO2. if you actually look at the amount of CO2 exchanged between blood and air, it's very different. Um, of the CO2 that physically enters alveolar air, only 70% comes from carbonic acid. So 90% of your CO2 is transported as bicarb, but only 70% of the CO2 moving into your air comes from that bicarbonate. 23% of the CO2 in your alveolar air actually came from a carbamino compound, and 7% came from dissolved CO2 gas. So what this means is your blood gives up dissolved carbon dioxide and CO2 from your carbamino compounds more easily than the CO2 that's being carried as your bicarbonate. Now, there is one major factor that can affect your CO2 transport. It's described as the Haldane effect. Now, low levels of oxyhemoglobin actually allow for greater blood CO2 transport. Now, if you have low oxyhemoglobin, that means you have high deoxyhemoglobin. Now, if you're looking at the symbols on the page, HHB actually means it's deoxygenated hemoglobin. HbO2 is oxygenated hemoglobin. So if you have low oxy, you have high deoxy. And oxyhemoglobin does not bind carbon dioxide as well as the deoxyhemoglobin. So the more deoxy you have, the more CO2 transport you can do. Also, deoxyhemoglobin binds more hydrogen ions than your oxyhemoglobin, and owing to this, the more deoxyhemoglobin you have, the greater your bicarbonate production is going to be. It's going to actually push that chemical reaction to the right, leading to the production of more bicarb, meaning greater CO2 transport. All right, so you now know how you breathe. You know how gases are exchanged, both in alveolar gas exchange and systemic gas exchange. You've learned the highlights of oxygen and CO2 transport and what can influence them. Now we need to talk about how is it regulated. We need to talk about the neural controls of breathing. Now, neural control of breathing is actually going to exist at two different levels. There is some cerebral control, which is conscious. So you do have the ability to inhale and exhale at will. So you can kind of hijack control over breathing. However, what we usually do is more unconscious and automatic. So this is when you breathe without thinking about it. So think of breathing as something you will automatically do, and if you decide that you want to take control, you can. Now, we're going to use some brainstem respiratory centers that are located in the reticular formation of your medulla oblongata and your pons in order to regulate respiration, in order to regulate breathing. What we're going to start with is by talking about your respiratory rhythmicity centers, which are located in the medulla oblongata. Now, your respiratory rhythmicity centers have the ability to control the basic pace and depth of respiration. So think of these as the centers that actually make you breathe. And they're active during both quiet and during forced breathing. Now, there has been new scientific discoveries about how these respiratory rhythmicity centers work. Your Saladin textbook is fully updated to match all of this new science. Actually, the reason that I was able to get the college to change to the Saladin textbook is that the book that we did use prior to this in 2 editions had never updated. So I actually had to tell students to not read a full section of their book because it was not scientifically accurate. So everything that you've got in Saladin, 100% spot on. Now, when you look at your respiratory rhythmicity centers, each center contains 2 groups. One group is called the ventral respiratory group, or VRG. This is the group that actually sets the base respiratory rhythm. So this is the group that makes you breathe. So it's what runs all of your quiet respiration, that nice subconscious automatic breathing. And in this group, you're going to have 2 different types of neurons. You have inspiratory neurons, or I neurons, and you have expiratory neurons, which are abbreviated E neurons. So what's going to happen is at the beginning of a respiratory cycle, the inspiratory neurons are going to turn on, and they are going to fire off action potentials for about 2 seconds. These action potentials are going to trigger your diaphragm and your external and internal intercostal muscles to contract. So they're going to stimulate inspiration to occur. Now, at the end of that 2 seconds, as the inspiratory neuron activity decreases, your expiratory neurons turn on and fire for about 3 seconds. Now, they're going to shoot off action potentials that are actually going to inhibit your inspiratory neurons. So they're going to turn off the eyes. What this is going to allow to happen is it's going to allow your respiratory muscles to relax. And when you relax, you're going to have your exhalation. So think of your ventral respiratory group as that basic pattern. The eyes turn on and you inhale. The E's turn on and you exhale. So it's like a little beautiful on-off switches that are going to drive your respiration. Now, the activity of the VRG can be altered. For example, there is what is called the dorsal respiratory group, which is also in that respiratory rhythmicity center. The dorsal respiratory group has the ability to change the rate of ventral respiratory group function based on different conditions and information. It can create fast, shallow breathing or slow, deep breathing. Now, it will make a decision on how to influence based upon the information it receives. The dorsal respiratory group is going to get information from lower brain areas, areas like your pons, the anterior portion of your medulla oblongata. It receives information from chemoreceptors that are in your major arteries. It even gets information from stretch receptors and irritant receptors in your airways. So the dorsal respiratory group is getting information about changes that have occurred within the body. So it's looking at blood CO2 levels, blood pH. It's looking at the stretching of the major airways as you're breathing. And that information is going to feed in to your DRG, and it will then adapt your breathing to suit those physiological changes. Now, within your pons, you have another group. It is called the pontine respiratory group, or the PRG. The PRG can also modify the rate of VRG function, and to a degree the DRG as well, except it's going to modify its function due to input from higher brain areas. Your pontine respiratory group is going to get information from the hypothalamus, your limbic system, your cerebral cortex, and then it's going to send its input to those lower brain areas in the medulla oblongata. And again, you're going to be able to hasten or delay your transition between inspiration and expiration to get shorter, shallower breaths, longer, deeper ones. And you can use this control to adapt your breathing to special circumstances. You breathe differently when you sleep or exercise. If you think about vocalizing, just how you talk or sing requires control over respiration, over your vocal folds. Even your emotional responses, involve changes in breathing. Have you ever heard anyone talk and cry where it's, no, no, I can't, oh. I mean, if you've ever heard anyone try to speak when they're crying, it's very ragged breathing. All of that is coming through the pontine respiratory group. It basically, in summary, allows your higher brain to influence your breathing. Now, the input to your respiratory centers comes from a lot of different areas. You've got central chemoreceptors, which are in your medulla oblongata. So your medulla oblongata, through these receptors, actually monitors the pH of your cerebrospinal fluid. The pH of your cerebrospinal fluid reflects the carbon dioxide level in your blood. So it is a way for your medulla oblongata to know how much CO2 we have in the blood by looking at how it's affected the pH of your CSF. You also have peripheral chemoreceptors. They're located in your carotid and aortic bodies. For the most part, their primary role is pH detection, but they do some monitoring of blood CO2 and blood oxygen, but again, it's primarily pH. You have stretch receptors, which are located in the smooth muscle of your bronchi, your bronchioles, and your visceral pleura, and they respond during lung inflation and deflation, and they allow you to have what are referred to as your Heurig-Brewer reflexes. Now, in adults, these reflexes are going to function with extremes of breathing, so very forceful inhale, very forceful exhale. These reflexes are not part of quiet respiration. So think of these sort of as emergency procedures. In the inhalation reflex, if you think about you're inhaling with force, you're expanding your lungs to a greater degree, the one thing that you want to make sure that you do is stop inhalation before you overinflate. I mean, what happens if you blow up a balloon too much? It pops. Your lungs have a limit to how much they can stretch before those little alveoli start to rupture. So this reflex prevents overexpansion of your lungs during forceful inhale. And what happens is if the stretch receptors detect overstretching, they can actually create a reflex or initiate a reflex that will inhibit your inspiratory neurons and stop your inspiration, and you would automatically then begin to exhale. In the deflation reflex, you have the ability to inhibit your expiratory centers. So if you're forcefully exhaling, you can inhibit your expiratory centers and stimulate your inspiratory centers. So if you're exhaling more than you should, you have a way to put the brakes on that way as well. You have irritant receptors that that are found in the epithelium of your airway, and they respond to smoke and dust, pollen, cold air, excessive mucus production. And if you stimulate these receptors, The result is usually a protective reflex, like bronchoconstriction, shallower breathing, apnea, which is breath holding, or coughing. Um, Things that will prevent, these responses would prevent irritants from getting further into the respiratory tract and promote your ability to get it out of the respiratory tract. And you do have voluntary control. The voluntary control would come from your primary motor area of your cerebral cortex. And this voluntary control is limited, but it is important for things like singing, speaking, and breath holding. So you do have a degree of voluntary control. Now, blood gas levels do affect your respiratory rhythms, and blood gas levels do affect hydrogen ions. So we're going to kind of talk about pH as well. Now, hydrogen ion changes in your blood are actually the most potent stimulus for your chemoreceptors. Your central chemoreceptors actually produce about 75% of the body's changes in response to pH. Your peripheral chemoreceptors produce the other 25% of the response. Now, what these chemoreceptors will be responding to are acidosis and alkalosis. In acidosis, your blood pH has dropped below 7.35. The most common cause of acidosis is hypercapnia, which is an arterial partial pressure of CO2 over 43 millimeters of mercury. And your body's corrective response for hypercapnia is hyperventilation. By breathing at a higher rate, you can actually exhale more carbon dioxide gas. So if you have that elevated CO2, the hyperventilation will rectify it. If you're suffering from alkalosis, your pH is higher than 7.45, and the most common cause of alkalosis is hypocapnia, which is an arterial partial pressure of CO2 below 37 millimeters of mercury. Now, the corrective response for hypocapnia is hypoventilation, which is a reduction in respiratory rate. And by breathing less frequently, it allows for your carbon dioxide levels to accumulate so that your CO2 levels get back up to homeostasis. Now, carbon dioxide's primary effect on respiration is indirect, and it's through pH. Because remember, most of your CO2 transport is going to be as bicarbonate, and when you form the bicarbonate, you do form the hydrogen ions. However, CO2 may directly stimulate your peripheral chemoreceptors and trigger an increase in ventilation. Now, oxygen really does not significantly affect respiration unless the partial pressure of oxygen drops below 60 millimeters of mercury. So oxygen is not the strongest signal with regards to affecting respiration. Now, a moderate drop in oxyhemoglobin allows for you to actually bind more hydrogen ions. And if you bind more hydrogen ions, your pH increases, so it creates alkalosis, which you just heard causes hypoventilation, a decrease in respiratory rate. However, if your partial pressure of oxygen drops below 60 millimeters of mercury, the hypoxemia that you've now created can stimulate your carotid bodies, override this inhibitory effect caused by the pH increase, and actually lead to an increase in respiration rate. Now, if you start thinking about respiration and exercise, it's kind of interesting. Even with exercise, your blood gas levels stay fairly stable because motor commands from your cerebral cortex are going to be sent to your respiratory centers. And what this allows is it allows your respiratory centers to anticipate the fact that you're going to be moving your muscles more vigorously and actually increase your respiration rate before your gas levels are even impacted. You also have those lovely proprioceptors that are monitoring your joint and limb movements. They're also sending information to the respiratory centers, alerting them to the fact that you're moving more vigorously, which allows for you to increase your respiratory rate before the movement gets vigorous enough to impact your gas levels. So when people do think about exercise, they automatically start thinking, oh, well, I'm exercising, my oxygen levels are decreasing, my CO2 is increasing. There's really not a big difference because of all of these preemptive changes to respiration, in anticipation of the movement. Now, recall from a previous exam that you learned about baroreceptor reflexes. And these reflexes, as we learned about them before, help to regulate your blood pressure if your blood pressure were to increase or decrease above or below homeostasis. However, they also will impact respiratory rates. For example, if your blood pressure falls or decreases below homeostasis, you learn that there would be an increase in sympathetic activity to help raise your blood pressure back to homeostasis. Well, that increase in sympathetic activity also increases respiration rates. You also learned if your blood pressure rises above homeostasis, that you have an increase in your parasympathetic activity. Well, the increase in parasympathetic activity leads to a decrease in the respiration rate. You also have some protective reflexes built in. You've got sneezing, which is triggered by irritants in the nasal cavity. You have coughing, which is triggered by irritants in the larynx, trachea, or bronchi. The sneeze or the cough, believe it or not, very similar process. What you would have is a brief apnea, so a brief cessation to breathing, followed by a very forceful exhale that has actually been clocked at about 99 miles per hour. You then also have something called a laryngeal spasm. Your larynx, which you might refer to as the voice box, has a lot of smooth muscle within it. And if you were to get chemicals or fluids or a foreign object into the larynx, into the glottis, the opening within the larynx, these muscles actually will contract and close your airway temporarily. Now, the feeling that you would probably have with a laryngeal spasm is kind of that choking sensation where you just feel like you're being strangled. However, that brief period of feeling like you're choking would then be followed by a very forceful cough. So think of laryngeal spasm as a temporary fix to prevent what has gotten into your larynx from going further in the respiratory tract. And then the follow-up cough would be used to blow it out of the larynx, hopefully out of the respiratory tract as a whole. Now, I did want to talk a little bit more about the voluntary control over respiration. This voluntary control involves your conscious thoughts. And your conscious thoughts would actually be relayed to your hypothalamus. Your hypothalamus would then relay this information down to your pontine respiratory group. And by having this voluntary control, we have the ability to keep water or irritating gases that we are consciously aware of out of our lungs. So if you wanted to go swimming, what do you do before you go underwater? You take a deep breath and hold it. And you make the conscious decision to do that. Now, while you're underwater, do you start breathing? And the answer is no. You hold it as long as you possibly can. When you can't hold your breath any longer, you come up for air. So that's your conscious thoughts keeping your breathing, from going so that you don't get water in your lungs. If you've gone into any bathroom on campus in the middle of the day, there can be some very nasty smells coming from those bathrooms. And a lot of times, you might hold your breath to avoid having to smell something unpleasant in your environment. And you hold it, hopefully getting in and getting out of wherever you are before you need to start breathing again. Now, your control is limited based on the buildup of CO2 and hydrogen ions. Remember, if you're holding your breath, you are not exhaling your waste gas. You are building up CO2, meaning you're building up hydrogen ions, you're becoming acidotic. And at some point, your inspiratory areas will be so strongly stimulated that they're going to trigger breathing regardless of your desire. So you do have the ability to regulate, but it's not limitless. And that's actually for your benefit, because if you are allowed to have total control over something so crucial for your survival, you would abuse the privilege and potentially kill yourself. There was a swimmer at the Sarasota Y, was it a little over a year ago, who was doing the underwater breathing training, where they would actually try to swim the full 50-meter length and then back, like do the full 100-meter back and forth across the pool underwater. And he was there by himself and was underwater swimming and had too much of a CO2 buildup and started to breathe while he was underwater. He lost control. His medulla oblongata created respiratory cycle to go, and he drowned. No one noticed that he wasn't moving in time to get him out of the pool to resuscitate him successfully. So you do have limited control. If you're ever dealing with a small child and they say they're going to hold their breath until you give them whatever they want, let them. Just make sure that they are sitting on some furniture or you are nearby to catch them, because they will hold their breath and they will build up their CO2 and their hydrogen and most likely pass out due to the excessive buildup of CO2, and they will just start breathing once they're unconscious. So, again, you don't want them to fall over and hit the floor, so just stay nearby. My daughter never tried it, but if she ever did, I'd let her pass out, and then she would know it wouldn't work. Also remember that your limbic system is your emotional brain. So because of this voluntary control, your emotional stimuli can alter your respiration. And even just anticipating strenuous activity can alter your respiration so that your blood gas levels are not impacted by the physical activity. Now, these particular influences on respiration are not in the Saladin textbook. These are from another book, but I find them very clinically relevant and kind of quirky. So I do include them in. So you won't find these referenced in your book. So this is it. And you want to make sure you have this information written down for your test. Body temperature changes will in fact affect your respiration. An increase in body temperature increases your respiration rate. A decrease in body temperature will decrease your respiration rate. Now, if you think of this in terms of a patient who has a really high fever, that high fever is actually going to cause an elevated respiration rate. With regards to the decrease in body temperature, have you ever jumped into a really cold swimming pool? And the moment you hit that cold water and come up, you go, and it's almost like you catch your breath. Well, that actually is a reflex response to sudden cold. A shock of sudden cold actually triggers a brief apnea, a brief cessation of breathing. Different types of pain trigger different respiratory effects. A sudden severe pain actually will cause a brief apnea, the same as the shock of the sudden cold. Prolonged somatic pains. So remember, somatic implies skin, skeletal muscle, and joints. Prolonged somatic pain actually increases respiration rates. So people who have had severe burns to their skin tend to have elevated respiration rates. Whereas visceral pain, so visceral implies it's coming from an internal organ, actually decreases your respiration rate. So depending on the source of your patient's pain, you need to be flexible in understanding what is that respiratory response healthy. Also, you have what are called anal sphincters. Sphincters are rings of smooth muscle, and surrounding your anus, you have an internal anal sphincter, which is made out of smooth muscle, and an external anal sphincter, which is made out of skeletal muscle. And these sphincters are going to keep the anus closed and by contracting, and then when you need to defecate, they will relax and open and allow for defecation. Now, what a lot of people don't know is that manually stretching that sphincter, so having something passing through the anus, physically stretching the opening, having stretch on those rings of muscle, actually increases respiration rates. Now, this is a hardwired reflex, meaning you're born with this reflex and you still have it right now. Now, it's a very useful reflex when you're dealing with newborn infants that have stopped breathing. You can manually insert a finger into their anus. I know, as gross as it might sound, but by manually stretching that sphincter, you can actually trigger respiration to begin again. So this is sort of like an emergency procedure. And this would also work in an adult who has stopped breathing as well. Now, granted, if you have someone who has stopped breathing out in public, pantsing them and trying to initiate this reflex, not exactly appropriate in polite society. But if you have a patient on a table and they're in a gown and you do have access, this is a reflex that could possibly be used to stimulate breathing in that unconscious, non-breathing individual. So your body has a lot of very interesting functions, some of which very few people know about, and you just have happened on the instructor that is aware of this one.